I'm Wesley Wooden. This is my team's power grid that we built. These are 2 huts. These are 2 more huts. And then this is a marketplace. These 2 huts are in phase with each other. These 2 huts are in phase with each other. And this is a 3rd phase. Using a 3-phase power design, we've created 4 different times of day represented by the green, yellow, blue, and red light. And then we show what our grid can do with this white light by balancing out the loads. As you can see, when we go through the day, the lights start on in the morning, and then this is the middle of the day, and the market's lights are still on. We have inductors representing refrigerators, and then in the houses we have ovens represented with resistors and capacitors representing phone chargers. So this is midday. This is evening. This is when everyone gets home from work and their lights are going on and the ovens are on for dinner. And then this is night, when the phone chargers are being used and when the market's refrigerators are being used. Now we'll go back to morning and show what our project can do. So now, as you can see, the white light's on, meaning that it's power correcting. So this is morning. As you can hear, the load is definitely better for our generator here because it's requiring less energy that's not in phase and efficient with each other. This is midday, this is evening, and this is night. And just again to see the difference, this is when the power is corrected, and this is when it's not corrected. Now I'm going to hand it off to Emerson.
So I'm Emerson, and I'm going to show you the power balancing of the phases. So if we go over down to multi-sim, it looks a little hectic. It's running right now, but if we go over and look at phase 3, this is before we've corrected it, and our power factor is at a 93%. Now this is below what we want, and it's not as efficient as could be. So here, because the capacitors are running, and right now we have all the loads on and simulating like a midday or evening. And so if I go and correct it, our power factor should change back up to just over 98%, which is just above our target range. Now all 3 of these are power corrected using inductors to correct capacitors and capacitors to correct inductors. So in the marketplace we have a capacitor to correct the 2 refrigerators that are almost always running, and these 2 phases are virtually exactly the same, as they both are just huts with inductors correcting the capacitors. Now if we go on over to the model, the real life model, so here we can see the phases are actually in phase. The yellow right here is the voltage, blue is the current. Currently we have it corrected for the nighttime, so this is what our load would look like if we did not correct anything. The voltage is very high and our phase is just slightly out of phase. Now if we were to correct it, everything pops back. The sizing is a lot better for the difference in the balance between the voltage and the current, and you can see our phase is virtually the same, as the peaks are very close to each other. And this is the 98 power factor which we have. Now if we go over to a different phase, I'll change up some of the wiring. So here's the uncorrected phase, the slightly shifted over, and sorry, I mixed that up. This is actually the uncorrected phase, and now the phases are corrected. They're now in sync with each other, and within that 98 to 100% power factor.
Thank you for seeing our project.
Have a good day.